The morning of October 3rd, 1943, and Group Captain Percy Pickard watched mechanics roll a completed de Havilland Mosquito onto the tarmac at RAF Marham. The bomber gleamed in pale grey camouflage, its twin Merlin engines silent, its sleek fuselage smooth as polished furniture. Which made sense, because 3 months earlier, that aircraft had been chair legs and piano keys. The officers from the Air Ministry had called it impossible. You couldn't build a combat bomber from plywood and glue. Wood belonged in cricket bats and rowing shells, not military aircraft streaking through German airspace at 400 miles per hour. The entire British aviation establishment had rejected the concept when Geoffrey de Havilland first proposed it in 1938, and for good reason. Every modern air force in the world had spent the 1930s transitioning from fabric and wood biplanes to all-metal monocoque construction. The Americans flew aluminum fortresses, the Germans built steel-skinned Heinkels. Even the Spitfire, Britain's pride, was stressed aluminum wrapped around a metal frame. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. And now de Havilland wanted to go backward? To build a frontline bomber using materials that furniture makers stocked in their warehouses. The Air Ministry's response was predictable and blunt. At a meeting in early October 1938, Ministry officials listened to Geoffrey de Havilland's presentation with thinly veiled skepticism. When he finished, they suggested the de Havilland Company would serve Britain better as a subcontractor, building metal wings for other manufacturers' bombers. They showed no interest in a wooden aircraft. The meeting lasted less than an hour. De Havilland went back to his drawing boards anyway. He'd been building aircraft since 1910, when he'd constructed his first airplane in a rented workshop using a 50-horsepower engine and fabric-covered wooden frames. That aircraft had crashed on its maiden flight, nearly killing him. He'd climbed out of the wreckage, started over, and eventually became one of Britain's most respected aircraft designers. His DH-88 Comet Racer had shattered speed records in 1934. His DH-91 Albatross airliner could cruise at 210 miles per hour, faster than most contemporary bombers. Using an innovative wooden construction technique developed by his chief draftsman, Arthur Hagg. Hagg had created something remarkable for the Albatross. Instead of traditional wooden framework covered with fabric, he'd designed a composite sandwich structure. Ecuadorian balsa wood, incredibly light but structurally weak, compressed between sheets of Canadian birch plywood, strong but heavy. The balsa provided thickness without weight. The birch provided strength without bulk. Together, formed into curved shells inside concrete molds and bonded with casein glue derived from milk protein, they created a structure with a strength-to-weight ratio equal to aluminum. Hagg had left de Havilland in 1937, but his technique remained, and Geoffrey de Havilland believed it could work for military aircraft. The argument was simple mathematics. Britain would go to war with Germany eventually, probably soon. When that war came, aluminum and steel would become strategic materials, rationed and scarce, demanded by tank factories and shipbuilders and artillery manufacturers. But wood? Britain had forests. Canada had forests. The supply was effectively unlimited. A wooden bomber could be built using materials that wouldn't compete with other war production. On July 7, 1938, de Havilland sent a letter to Air Marshal Wilfrid Freeman, the Air Council's member for research and development. He laid out his reasoning methodically. Aluminum, shortages would occur during wartime. Wood supplies would remain adequate. Although wood was inferior to metal in tension, its strength-to-weight ratio equaled or exceeded light alloys. Given these factors, a different approach to bomber design was possible. A fast, lightly built wooden aircraft using minimal strategic materials could outperform heavier metal bombers through superior aerodynamics and reduced weight. Freeman was intrigued, but he was one man in a bureaucracy that viewed metal construction as the obvious future. The RAF's design philosophy emphasized heavily armed bombers with defensive gun turrets, armor plate, and self-sealing fuel tanks. Weight was acceptable if it provided protection. De Havilland's concept went the opposite direction. No defensive armament at all. No turrets, no armor, no compromises to aerodynamics, just speed. The bomber would be so fast that enemy fighters couldn't intercept it, making defensive guns unnecessary. It was heresy to the air, Ministry's established thinking. Bomber Command had already learned painful lessons about inadequate defensive armament. Their Fairey battle light bombers, deployed in France in 1940, had been slaughtered by German fighters precisely because they lacked sufficient guns. Now de Havilland wanted to build a bomber with no guns whatsoever? The Ministry filed his proposal and moved on to more conventional projects. De Havilland kept working. Through 1939, as war with Germany became inevitable and then actual, he refined his design. A twin-engine aircraft, powered by Rolls-Royce Merlin engines, the same power plants used in Spitfires and Hurricanes. Crew of 2, pilot and navigator, sitting side by side. Bomb bay capable of carrying 1,000 pounds internally, with provisions for additional external stores. Estimated top speed, 390 miles per hour at altitude. Range, 1,500 miles. The critical specification was that top speed. In September 1939, when Britain declared war on Germany, the Luftwaffe's primary fighter was the Messerschmitt Bf 109E, with a maximum speed of 354 miles per hour. The Focke-Wulf Fuvue 190, Germany's next-generation fighter, wouldn't enter service until 1941. If de Havilland's estimates were correct, his wooden bomber would be faster than any fighter aircraft currently defending German airspace. Speed would be its defense. Freeman continued pushing for the project behind the scenes. By December 1939, 4 months into the war, the Air Ministry finally agreed to examine a full-scale mock-up. Company representatives, ministry officials, and RAF operational commanders gathered at de Havilland's Hatfield facility on December 29th to inspect the prototype. The design team had built it in secret at Salisbury Hall, a 17th-century manor house a few miles from the main factory, using the building's large kitchen as a workshop. The mock-up impressed the visitors enough to warrant further consideration. On January 1st, 1940, Freeman chaired a decisive meeting with Geoffrey de Havilland, John Buchanan from the Ministry of Aircraft Production, and Buchanan's Chief of Staff. De Havilland made his case one final time. His aircraft would be the fastest bomber in the world. It had to be useful. Freeman supported him, and on March 1st, 1940, the Ministry issued official specification B1/40/DH, authorizing construction of a single prototype for an unarmed bomber reconnaissance aircraft. Construction began in March 1940. Then came Dunkirk. Between May 26th and June 4th, the British Army evacuated from France, leaving behind nearly all its equipment. Britain stood alone against Germany, invasion seemed imminent, and the Ministry of Aircraft Production under Lord Beaverbrook made a brutal calculation. Every resource had to focus on producing fighter aircraft immediately. The Mosquito project was cancelled. The design team was ordered to stop work and redirect their efforts to building Tiger Moth trainers and other existing types. Air Vice Marshal Freeman quietly ignored that order. He didn't pass the cancellation down the chain of command, and the Mosquito team at Salisbury Hall kept working through the Battle of Britain. They lost time to air raids, spending hours in shelters while German bombers targeted nearby facilities, but they continued fabricating components and assembling the prototype. By November, they were ready. On November 19, 1940, workers transported the completed prototype by road to a hangar at the de Havilland factory at Hatfield. The aircraft, designated W4050, bore the serial number E0234 and was painted overall bright yellow for visibility during flight testing. 6 days later, on November 25th, Geoffrey de Havilland Jr., the founder's son and the company's chief test pilot, climbed into the cockpit alongside engine installation designer John Walker. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The Mosquito prototype lifted off from the short grass strip adjacent to the Hatfield factory just before noon. De Havilland flew for 35 minutes, testing handling characteristics, checking control responses, evaluating the aircraft at various speeds and configurations. When he landed, his report was concise and enthusiastic. The aircraft handled beautifully. It was faster than any bomber he'd flown. It felt right. Formal performance testing began in February 1941 at the RAF's evaluation facility at Boscombe Down. The trials silenced every skeptic. At 22,000 feet, with two Merlin 21 engines producing 1,460 horsepower each, the prototype reached 392 miles per hour in level flight. That speed made it faster than the Spitfire Mark II, the RAF's primary fighter at the time, despite the Mosquito weighing twice as much and having twice the wingspan. The wooden bomber was outrunning fighters. The construction technique that made this possible seemed absurdly simple. In furniture factories across High Wycombe, Buckinghamshire, workers who'd spent decades crafting dining room chairs and upholstered sofas learned to build aircraft fuselages. Companies like Parker Knoll, E. Gomme, and Waring and Gillow, prestigious names in British furniture making, converted their production lines from civilian goods to military components. Piano makers and cabinet makers and coach builders all contributed parts. Around 5,000 of the 7,781 Mosquitos eventually built contained components manufactured in High Wycombe workshops. The fuselage construction process started with massive concrete molds, each holding one half of the fuselage split vertically along the center line. Workers began by installing 7 bulkheads, internal frames made from plywood, skins separated by spruce blocks, positioned precisely within the mold. Then came the inner plywood skin, shaped birch sheets glued and screwed to the bulkheads using hundreds of small brass fasteners. Once the inner skin was secured, craftsmen fitted the core layer. This required cutting and shaping balsa wood strips to fill the spaces between structural members, essentially creating a lightweight sandwich filling that would provide thickness and insulation without adding significant weight. Ecuadorian balsa, shipped across the Atlantic despite U-boat threats, was selected specifically for its combination of extreme lightness and adequate compression strength. Each piece had to be custom fitted, dry tested, adjusted, then glued in place. After the balsa core was installed, workers applied the outer plywood skin, more Canadian birch sheets, more casein glue, more brass screws, all clamped in place with spring steel straps that held the entire assembly tight against the mold, while the glue cured. Some factories used concrete molds with internal hot water pipes to accelerate curing. Others used heat lamps. The process took hours, sometimes days, depending on ambient temperature and humidity. When the glue had fully cured, both fuselage halves were removed from their molds. Workers cut sawtooth joints along the upper and lower edges where the two halves would mate. While the fuselage shells were still open and accessible, technicians installed electrical wiring, hydraulic lines, pneumatic controls, flight control cables, everything that would be difficult or impossible to access once the fuselage was sealed. Small-statured workers were specifically selected for this task because they could maneuver inside the tight confines more easily. Finally, the two halves were brought together, glued along the sawtooth joints, and screwed tight with additional brass fasteners. The fuselage contained roughly 20,000 screws total, each one reinforcing glue joints that might fail under combat stress. The completed fuselage shell was covered with doped madapolum fabric, a fine cotton weave that provided a smooth aerodynamic surface and additional protection from moisture. Wing construction followed similar principles, but used different materials and techniques. Unlike the fuselage, which was built in 2 halves, each wing was constructed as a single unit spanning from wingtip to wingtip, one continuous structure. The internal framework consisted of 2 large plywood box spars running fore and aft, essentially hollow beams that provided the primary load-carrying structure. Plywood ribs and stringers connected the spars, creating the wing's airfoil shape and providing attachment points for fuel tanks, engine mounts, and flight controls. The wing skinning used birch plywood, 1 layer on the bottom surface, 2 layers on the top. Between the 2 top layers, Workers installed additional fur stringers for reinforcement because the upper wing surface carried the heaviest aerodynamic loads during flight. The entire structure was glued and screwed together using approximately 30,000 brass screws per wing. 30,000. Every screw placed by hand, every joint checked, every rivet backed by wood rather than metal. The completed wing weighed significantly less than an equivalent metal structure while maintaining comparable strength. Load testing demonstrated the wing could withstand high-G combat maneuvers even when loaded with thousands of pounds of fuel and bombs. The smooth plywood surface, carefully sanded and finished, produced remarkably low drag. No protruding rivet heads, no panel gaps, no surface irregularities. The aerodynamic efficiency was exceptional. Metal was used only where absolutely necessary. Engine nacelles required metal cowlings to handle heat and protect against fire. Engine mounts, load-bearing brackets, landing gear, doors, control surface frames, all metal. But the primary structure, the parts that gave the aircraft its shape and strength and carried the loads in flight, was wood. Specifically, it was Ecuadorian balsa, Canadian birch, English ash, Alaskan spruce, Douglas fir, all bonded together with glue and screws into a composite structure that outperformed aluminum in every metric that mattered for a fast bomber. The skeptics at the Air Ministry had been wrong about almost everything. They'd been wrong that wood was obsolete for military aircraft. They'd been wrong that an unarmed bomber couldn't survive over Germany. They'd been wrong that conventional furniture makers couldn't build precision aircraft components. But they'd been right about one thing. It did sound absurd. And in March 1943, when Mosquitos began regular operations deep into German airspace, it drove the Luftwaffe commander absolutely furious. Hermann Göring, Reichsmarshal of Germany and commander of the Luftwaffe, had a problem he couldn't solve. On January 30th, 1943, the 10th anniversary of the Nazi Party's seizure of power, he was scheduled to deliver a speech from Berlin's main broadcasting station. The speech would be transmitted across Germany, a propaganda opportunity to rally the nation after the disaster at Stalingrad. Göring arrived at the broadcasting headquarters early that morning, prepared his notes, and waited for 11 o'clock. At precisely 1100 hours, air raid sirens wailed across Berlin. 3 Mosquito bombers from 105 Squadron RAF, led by squadron leader Robert Reynolds, streaked over the German capital in broad daylight. They were flying at 25,000 feet, moving at approximately 400 miles per hour, and German fighters scrambled from nearby airfields couldn't reach them in time. The Mosquitos dropped their bombs on the broadcasting station and turned for home. All 3 aircraft escaped. Göring's speech was delayed by over an hour. When he finally took the microphone, he was, according to witnesses, boiling with rage and humiliation. The entire Nazi leadership had gathered to commemorate their anniversary, and enemy aircraft had bombed Berlin in daylight while they watched helplessly. It made a mockery of Göring's boast 3 years earlier that if a single Allied aircraft reached the Reich, Germans could call him Meyer, a common Jewish surname intended as the ultimate insult. That afternoon, 3 more Mosquitos from 139 Squadron hit Berlin again, this time targeting the Sportpalast, where Propaganda Minister Joseph Goebbels was addressing a massive rally. Once again, the bombers arrived, dropped their ordnance, and disappeared before fighters could intercept them. German civilians looked up at vapor trails scratching across the sky, while their leaders promised victory and invincibility. The psychological impact was devastating. 3 weeks later, on March 18, 1943, Göring summoned Germany's aviation industry leadership to his hunting lodge at Karinhall, deep in the Schorfheide forest. The meeting lasted 6 hours. A stenographer recorded every word. At one point, Göring turned his fury specifically toward the Mosquito, and what he said revealed the depth of German frustration with an aircraft they couldn't counter. The exact wording has been disputed by historians, but multiple sources from German aviation conferences in 1943 confirm Göring's obsession with the Mosquito, and his green and yellow envy, quote, has been attributed to him by multiple wartime accounts. At that March 18th meeting, he complained bitterly about the wooden aircraft that was tormenting his air defences. The British had built something primitive and fast, using materials Germany desperately needed for aircraft but couldn't spare. Piano factories were producing bombers, furniture makers were building warplanes, and those wooden aircraft were flying over Germany with impunity. The Luftwaffe's problem wasn't just psychological. It was mathematical. When the Mosquito entered service in 1942, it was approximately as fast as the German fighters opposing it. The Bf-109F had a top speed of 379 miles per hour. The F-80-190A could reach 385 miles per hour. Early Mosquito bomber variants topped out around 390 to 400 miles per hour. The speed differential was small, perhaps 10 to 20 miles per hour, but critically, that differential existed at the Mosquito's cruising altitude. Fighter interception required more than just matching top speed. German fighters on the ground needed time to scramble, climb to altitude, position themselves, and close on the target. Mosquitoes flying reconnaissance or bombing missions would already be at operational altitude when detected, moving at maximum cruise speed toward the target. By the time fighters climbed to intercept altitude and accelerated to combat speed, the Mosquito was often already over the target and turning for home. German fighter pilots developed tactics specifically for hunting Mosquitoes. They'd position fighters along known return routes, waiting at altitude, diving from above to build speed before attacking. Heinz Nock, a Luftwaffe ace, managed to shoot down a Mosquito by closing his cooling radiators to prevent overheating, using emergency boost to squeeze every possible mile per hour from his Bf-109, and pushing his engine to the edge of destruction just to get within gun range. His wingman couldn't keep up and fell behind during the chase. Even when fighters successfully intercepted Mosquitoes, the wooden construction proved difficult to damage critically. Cannon shells often passed through the plywood and balsa without causing catastrophic structural failure. The sandwich construction absorbed impacts differently than metal. A 20mm shell that would tear through aluminum ribs and spars might punch a hole through plywood, shred some balsa, and exit the other side without compromising the aircraft's airworthiness. Pilots reported hitting Mosquitoes with multiple cannon rounds and watching them continue flying. The agility of the aircraft surprised German pilots. Mosquitoes could turn surprisingly tight for a twin-engine bomber, tight enough that pursuing fighters had to be careful not to overshoot. In several documented engagements, Mosquito pilots outmaneuvered four 190s by entering steep climbing turns, forcing the German fighters to either break off or risk stalling. The Mosquito's power-to-weight ratio, achieved through the lightweight wooden construction, gave it performance characteristics closer to a fighter than a bomber. Later variants became even faster. The Mosquito B Mark 9, introduced in 1943, achieved 408 miles per hour at altitude. The pressurized high-altitude versions could cruise at 350 miles per hour at 30,000 feet, well above the effective ceiling of most German fighters. By 1944, when Germany introduced the PLYWOOD with improved performance, the war was essentially lost. The most advanced German piston-engine fighters could match or slightly exceed Mosquito speed, but they arrived too late and in too few numbers to matter. The Mosquito's speed advantage meant it could operate in ways no other bomber could. Low-level precision raids became a specialty. On September 25, 1942, Mosquitoes from 105 Squadron attacked the Gestapo headquarters in Oslo, Norway, flying at treetop height through narrow fjords, approaching the target at less than 50 feet altitude, releasing bombs that struck the building with devastating accuracy and escaping before German defenses could respond. The entire raid lasted minutes. But the mission that would make the Mosquito legendary came on February 18, 1944. The target was Amiens prison, in northern France. Intelligence indicated that over 100 French resistance members were scheduled for execution on February 19th. Among them was Raymond Vivant, a resistance leader who knew critical details about Allied invasion plans. If the Germans discovered his identity and interrogated him, the damage to Operation Overlord could be catastrophic. The RAF designated the mission Operation Jericho, after the biblical city whose walls fell to Joshua's army. 18 Mosquito FB Mark VIs, from 3 squadrons, 464 Squadron Royal Australian Air Force, 487 Squadron Royal New Zealand Air Force, and 21 Squadron RAF, would attack the prison at lunchtime when guards were in their mess hall. The mission required surgical precision. The bombs had to breach the outer walls without destroying the main prison building and killing the prisoners they were trying to free. Group Captain Percy Pickard led the formation. Pickard was RAF royalty, holder of the Distinguished Service Order, with 2 bars and the Distinguished Flying Cross, famous for starring in the propaganda film Target for Tonight in 1941. He was experienced, respected, and about to fly the most demanding precision bombing mission of his career. The formation took off from RAF Hunsdon at 1100 hours on February 18th. Weather was atrocious, heavy clouds and snow squalls that scattered the formation over the English Channel. Several Mosquitoes lost contact and returned to base with mechanical issues. By the time the remaining aircraft crossed into France, the strike force had been reduced to 13 bombers instead of 18. They flew at wave-top height across the Channel, making landfall near Le Tréport, then turned east to confuse German fighter controllers before swinging southeast toward Amiens. The Mosquitoes descended even lower, barely clearing the poplar trees lining the road from Albert to Amiens. Pilots had to bank their wings to avoid hitting branches. The prison appeared exactly as briefed, a grim stone structure alongside the road, surrounded by high walls. 487 Squadron went in first, at exactly 12:01. 3 aircraft targeted the outer walls with 500-pound bombs fitted with 11-second delay fuses. The bombs penetrated the 3-foot-thick stone walls and detonated inside, blowing massive breaches in 2 locations. 464 Squadron followed 3 minutes later, targeting the guards' quarters and the main prison buildings. Bombs struck with devastating accuracy, destroying the German mess hall and killing or wounding most of the guards. Pickard circled at 500 feet, assessing the damage. He could see prisoners escaping through the breached walls. He radioed 21 Squadron, held in reserve, that their attack was unnecessary. The mission was complete. Then he turned for home. German fighters from Jagdgeschwader 26 had been scrambled when the raid began. They arrived as the Mosquitoes were departing. Oberleutnant Waldemar Radner led his Fubu 190 formation down through the clouds and spotted Mosquitoes and their Typhoon escorts below. He positioned for an attack, dove on Pickard's Mosquito, and opened fire. The 20mm shells severed the Mosquito's tail section. The aircraft crashed near the prison, killing both Pickard and his navigator, Flight Lieutenant Alan Bradley. The raid freed 258 prisoners. 102 were killed by the bombing, 74 were wounded, and 182 of the escapees were eventually recaptured. But several key resistance leaders, including Raymond Vivant, escaped and evaded capture. Post-war investigations questioned whether the raid was necessary, whether the executions were actually scheduled, whether the mission accomplished its stated objectives. But for the crews who flew it, Operation Jericho represented what the Mosquito could do that no other aircraft could. Precision strikes at impossible speeds against heavily defended targets, accepting losses but completing missions that conventional bombers couldn't attempt. The Mosquito's versatility expanded beyond bombing. Night fighter variants equipped with radar hunted German bombers over England and later over Germany itself. By war's end, Mosquito night fighters had claimed approximately 600 German aircraft destroyed, including 68 Fu-190s shot down in darkness. Photo reconnaissance Mosquitoes flew deep into German territory, photographing targets with minimal losses. They provided the intelligence photographs of Peenemünde that enabled the RAF to bomb Germany's V-2 rocket development facility in August 1943. Fighter-bomber versions carried 4 20mm cannons and 4 7.7mm machine guns in the nose, plus bombs or rockets under the wings. The Coastal Command variants hunted U-boats in the Bay of Biscay and attacked German shipping off Norway. One specialized variant, the FB Mark 10 ATI, mounted a 57mm cannon capable of destroying ships and submarines with single hits. The Pathfinder squadrons adopted Mosquitos as their primary marker aircraft. Flying ahead of the main bomber streams, Mosquito crews would locate targets and mark them with coloured flares, guiding the following Lancasters and Halifaxes to their aim points with unprecedented accuracy. The Light Night Striking Force, formed in 1943, consisted entirely of Mosquito bomber squadrons that harassed German cities nightly, forcing the Luftwaffe to maintain fighter defences across Germany rather than concentrating forces. Production numbers revealed the wooden bombers' success. Between 1940 and 1945, British, Canadian, and Australian factories built 7,781 Mosquitos in 43 different variants. Peak production reached over 400 aircraft per month in 1944. The furniture factories that skeptics claimed couldn't build precision aircraft were mass-producing bombers faster than metal aircraft factories could match their output. The Mosquito held several remarkable records. LR 503, nicknamed F for Freddy, A.B. Mark 9 bomber serving with 109 Squadron, flew 213 operational sorties during the war, more combat missions than any other Allied bomber. It survived the entire war only to crash during a Victory Bond Drive demonstration on May 10, 1945, 2 days after Germany's surrender, killing its crew. The loss rates told the story most clearly. Mosquito squadrons operating over Germany typically suffered loss rates between 1 and 2% per sortie. Lancaster heavy bombers in the same period averaged 4 to 6% losses per mission. The speed that Geoffrey de Havilland had promised in 1938 was saving lives exactly as he'd predicted. Aircraft that couldn't be caught couldn't be shot down. German attempts to counter the Mosquito largely failed. Göring ordered the formation of specialized Jagdgeschwader units, JG-25 and JG-50, specifically to hunt Mosquitos. These units achieved minimal success and were eventually disbanded. The Germans developed their own wooden night fighter, the Focke-Wulf Tar 154, attempting to copy the Mosquito's design philosophy. Production problems, glue failures, and inadequate performance doomed the project. Only a handful were built before the program was cancelled. The jet-powered Me-262 could catch Mosquitos, but Hitler insisted on deploying the 262 as a bomber rather than a fighter, limiting its effectiveness in the interceptor role. By the time 262 seconds were assigned to air defense in significant numbers, Germany was collapsing. Fuel shortages, pilot attrition, and overwhelming Allied air superiority meant that even when German jets could theoretically intercept Mosquitos, they rarely did. The wooden construction that everyone said was obsolete proved prophetically modern. In the 1970s, aerospace designer Burt Rutan would revolutionize home-built aircraft by developing composite sandwich construction, using foam cores and fiberglass skins, essentially the same structural principle Arthur Hagg had pioneered for the Albatross in 1935 and de Havilland had refined for the Mosquito. Rutan's Variéis and subsequent designs demonstrated that sandwich composites could produce lighter, stronger aircraft than conventional metal construction. Modern composite aircraft, from Boeing 787 seconds using carbon fiber to military drones using advanced laminates, trace their conceptual lineage directly to the Mosquito's plywood balsa plywood sandwich. The principle remained valid. Separate the structural loads between skins optimized for tension and compression. Fill the core with lightweight material that maintains spacing and resists shear. Bond everything together with adhesives strong enough to prevent delamination. What changed was materials. Carbon fiber instead of birch, foam instead of balsa, epoxy instead of casein. But the fundamental engineering was established by furniture makers in High Wycombe building bombers from chair components. The Mosquito remained in RAF service until 1955, a decade after the war ended. The last operational flight occurred in May 1963, when a target towing variant finally retired. Several Mosquitos flew in airline service with British Overseas Airways Corporation during the war, carrying VIPs and priority cargo between Britain and neutral Sweden. unarmed transports relying entirely on speed to evade German fighters over occupied Norway. Today, fewer than 40 Mosquitos survive in museums worldwide. 4 remain airworthy, preserved and maintained by organizations dedicated to keeping the wooden wonder flying. The prototype, W4050, the aircraft Geoffrey de Havilland Jr. first flew in November 1940, survives at the de Havilland Aircraft Museum in London Colney, the only Second World War British prototype aircraft still in existence. The Air Ministry officers who rejected the concept in October 1938 weren't stupid. They were making rational decisions based on established engineering practice and military doctrine. Metal construction was the future for aircraft design. They were right about that. But they failed to consider that sometimes the future arrives through unexpected paths, and that obsolete materials handled correctly can outperform modern ones handled poorly. Geoffrey de Havilland's wooden bomber succeeded not because wood was superior to aluminum, but because the design team understood exactly how to exploit wood's specific properties. The composite sandwich construction wasn't backward technology. It was advanced engineering using readily available materials. The furniture makers weren't unsuited to precision aircraft work. They were craftsmen with decades of experience working wood to tight tolerances, skills that translated perfectly to aircraft fabrication once they understood the requirements. The absurdity wasn't in the concept, it was in the execution. It was absurd that piano factories could outproduce aircraft manufacturers. It was absurd that furniture makers could build bombers faster than Germans could shoot them down. It was absurd that plywood and glue could create an aircraft that Hermann Göring, commanding the world's most advanced air force in 1940, couldn't counter with all of Germany's industrial capacity and engineering expertise. But the absurdity worked. For 7,781 aircraft across 6 years of production, the absurdity kept working. And it drove the Luftwaffe commander green and yellow with envy until the day Berlin fell and his air force ceased to exist. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.